Okay. So, very good morning to all of you. I would like to invite Professor Vinay Kumar, ex-scientist E and Technical Director, National Informatics Center, Government of India. Sir has completed MCA from JNU, New Delhi and PhD from Delhi University. Sir has worked as ex-scientist E and Technical Director for National Informatics Center, Government of India. Sir had also served the position of as a dean and professor in VIP New Delhi. Last but not the least, he is the founder of DHEI Research Foundation, New Delhi. He has published several research papers in international reputed journals. His achievement does not end here. His research paper entitled Proof of Beal's Conjecture and Fermat Last Theorem using Contra Positive method in 2018, in view of the fact that so many eminent mathematicians were unable to prove Fermat's last theorem. He has published uh, several books in the reputed publications. So now I would like to take this opportunity to do the honors. I request Professor Vinay Kumar to kindly start his lecture on evolution of digital electronics from basic concept of sets.
Thank you, Dr. Ratnesh Misra sir, and good morning to all participants that might be including the faculty members, the research scholars, students from the different engineering colleges and the other reputed institutions. And I hope this is the last day, so everybody must be bogged down. The mind is full with all the lectures and the concepts delivered during last 4 days on the mathematics. And mathematics itself is the, as per the feedback of the students whom I taught, it's a boring subject. So I can very well visualize. May I have the faces of the participants before I start presenting? Because now once we have the visual interaction, I hope that will be the better. Some people just switch on the video. I hope that will help a lot. Anyway, so that is that's the. It looks like I'm talking to somebody. Otherwise, look, I'm talking to the screen. Just a passage with the. So that is. So today we will be just discussing, and I will keep my presentation to the very basics, so that it should be just enjoyable for this 1.5 hour. Not very deep concepts, but I think you will enjoy this. And because I am starting with the very rudimentary concept which we are taught in the very school level, that is the set. And then I will drag you to the level of the fuzzy sets and the quantum theory, which is normally at the PhD and the research level. And I hope you will enjoy this journey. So let us start how this basic concept of set has really helped in evolving what this complicated circuitry of the computer science is there. I will be sharing some slides. And I hope it is visible.
Yes, sir.
So just is the test one, whether it is visible and it is appearing on the screen of everybody.
Yes, sir. Visible.
It's visible. Good one.
Visible, sir.
Okay, so that is the concept. And before, I should not just enlarge it to the complete screen. Am I right? I hope this is enough.
This is enough, sir.
This is enough. Good. So let us see. I think we all know, we have studied in our school days. If A is a set, but the basic concept in the set is that position of the element is not fixed. The only restriction we put over here, let us say this is the first element, second element, third element, and so on. so that the position of the element is fixed just for the representation purpose, nothing else. Otherwise, the set, the general meaning, we will continue with that. So let A be a set containing three elements, A, B, and C, where A is the first element, B is the second, and the C is the third element. So one thing, how this the binary concept has evolved from this one. Whenever we say this is the set concept, and then it's the subset, power set. So in any subset of the A, either A will be absent or it will be present. B will be absent or it will be present. C will be absent or it will be present. There is only two states. And if we represent the presence of the element in a set by 1 and the absence of an element by 0, then see the different just see this one. I hope it's visible.
Yes, sir. Visible.
So now the first subset, that is the null set. Now in this set, none of the element A, B, and C is present. So we can very well represent 0, A is absent, B is absent, and C is absent. Now let us see the subset A, the containing only elements A, means the first element is present, but the next two are not present. So we are writing it 0, 0. And so on, so on. In the seventh one, B and C, the B is present, so we are writing it 1 at the second position. C is present, we are writing it 1 at the third position, and the A is absent, so we have written it 0. What I mean to say, all these 8 subsets, possible subsets of the A, can very well be represented in form of the 0 and 1, that is the bit string. So see, there are the 8 subsets, we have the 8-bit string, and using the 3 bits, we have at the most the 8-bit strings only this many combination, and it's representing the different powers, different powers, the subsets of the A, set A. So this is the binary concept we have used. Anything to ask? Should I proceed further? Any query here? Any query? Otherwise, I will proceed further. Simply the conceptualization of the set, and we will discuss only 2-3 concepts over here. And the next slide, I will just show how this the basic quantified into the 2 level, that is the binary level. Entire computer which we are using currently, it deals with the binary concept only, bits 0 and 1, 0 and 1. And that's why I'm translating it into the 0 and 1. I hope it's okay. Anybody please?
Yes, sir.
Yes, sir.
Now, just see the next one. Now, let us correlate the concept of power set with that of bit combination that we study in our computer fundamental courses. We get a bit representation for every possible subset of A, the way I have shown, every possible combination of the elements of the set A. The length of each bit string is equal to the number of elements in A. The number of elements in set A is 3. So just see the length of the bit string of every such possible representation of the subset is now 3. If we have the 4 element, we get the bit string of the 4 bits, and so on, so on. Now you see the union, and see this one, union and the logical bit operator. Here itself I will represent, just conceptualize. If we take a union of A and B, then we will have a set this A and B. the union of the set containing only A, set containing only B, we will get a set containing in the fifth row, A and B. Fifth row, this one. And if we just do this bitwise OR, the 1 and 0, that is the 1, 0 and 1, that is the 1, and then the 0, 0, that will remain 0. Means ki the union concept, whatever we have studied in the set theory, this is nothing but the equivalent to the bitwise or the logical OR in the Boolean circuit or the Boolean algebra. Similarly, intersection of the set operation is equivalent to the AND of this one, the Boolean algebra. Similarly, see the complement. So here universal set is the A complement of the A set containing this subset only will have the set containing B and C. And now see the ones complement. सिर्फ जहाँ 1 है वहाँ 0 कर दीजिए, 0 है वहाँ 1 कर दीजिए. Then the ones complement of this one is nothing but they're going to be this one. That means even the complementation of the set can very well be represented using the ones complement in the Boolean algebra. So these are the basic operations which we derive from the basic operations on the set only. Just the correlation. Yeah, how this the Boolean algebra or the bitwise algorithm is just derived from the set operation. What we are going to cover in this lecture of the 1 hour, 1.5 hours, is just see this is the diagrammatic representation of the today's lecture plan, like the basic elements of the set, and these elements constitutes the set, and we will define one partial order relation. And we all know, I hope you must have studied, they say the set equipped with a partial order relation defined on this is together is called a partially ordered set. That is the poset we call it. Once this poset possesses certain properties, like if it is bounded, and every pair of element has a least upper bound and the greatest lower bound, then it gives the concept of the lattice. That is the meet and join. From lattice, we derive this is the finite Boolean algebra. This from finite Boolean algebra, we just see the how the circuitry design, the optimization, like the Carnot map, K map, and so on. From this, the large scale integration, very large integration, which gives you the computer system, and this computer system, which is an indispensable tool for all the research and development what we are doing today, including this the remote talk on this topic. We are using the computer or the logical circuit to deliver the lecture as well as to receive the contents of this lecture. Now, just see the evolution only. Let B. Now we are going towards the from the set. Yeah, B be a set containing two elements, 0 and 1. Be a set of bits, and the bits we call 0 and 1. This is the binary digits, so 0 and 1. And define Bn subscript Bn as a Cartesian product of the B set B, Cartesian product of the set B taken n number of times. So using this definition, B2 we can write B cross B, B3 we can write B cross 3, and so on up to n. Now, what are the elements? If you are writing B2 B cross B and we find this Cartesian product, then the B2 will have all these pairs. Similarly, if we take the B3, the Cartesian product of the B taken 3 at a time, then it will contain this triplet. All the basic things, Cartesian product we have studied, set, union, intersection. So just I am finding B equal to this one, we have multiplied, find the Cartesian product, the B, the 2 times, we have got this one. Similarly, we have multiplied B 3 times, so we have got this, the B, the 8. Now, what I am saying for the simplification purpose, we will convert the pair or the triplet into simply a bit string. Just see how we are doing. Simply just a simplification of the representation. Like now the B has become 0 and 1 and B2. In the B2, what I am doing? Yeah, in this pair, we have removed this parenthesis sign and dropped this comma. That this has become 0, 0. Similarly, dropping this comma and removing the parenthesis sign, it will become 0, 1, and so on, so on. Similarly, here in the B3, if we remove the parenthesis and drop these two commas, it will become 1, 0, 0. So all the elements here is nothing but the set of the bit string corresponding 0 and 1 in the B1. So this is the set of all the bit strings of length 1. The B2, this is the all possible bit strings of length 2, only 2 bits are there. B3, all the bit strings of length 3, only 3 bits are there in all these triplets. So this we have up to B1, B2, B3, we have come. Now let us come a little bit more we are doing now. Correct? So let Bn, using this concept, in general, we can define Bn as the set of the bit string x, such that x is a binary string of length n. Just see, in the B3, they say that every element is a bit string of length 3. In the B2, every element is a bit string of length 2. So here in the Bn, we can write x, the way x is a binary string of length n. And the number of elements in the Bn is how many it's going to be? If there are the 3 elements, 2 to the power 3. If there are 2 elements, 2 to the power 2. If there are n elements, so that is the 2 to the power n. So the number of elements in the Bn will be 2 to the power n, equivalent to, if you are given n bits, we can have the 2 to the power n total binary combinations, bits combination. Now we are defining one partial order relation. I hope this foundation up to here is okay. I hope up to this foundation we are proceeding well. Nothing, nothing very complicated. So now we are defining one partial order relation. We know what is the relation. What is the partial order relation? That is the 3 characteristics. It should property satisfy, it should be reflexive, it should be transitive, and it should be antisymmetric. So here, because every element is a bit string of length n, so we write it, let x and y be any elements of the Bn such that x equal to a1, a2, a3 up to n, and the y equal to b1, b2, b3, n, where a and the bi either 0 or 1, means they are the bit string of length n. This is also bit string of length n. Sorry, bit string of length n. Now we define this partial. Let this symbol be a partial order relation defined on the Bn such that for any 2 element x and y, this is the a1, a2, a3, and so on, x is related to y if and only if every bit in the x is less than equal to the corresponding bit in the y. For k equal to, simply we say that x will be related to y. This x will be related to y if every bit in x, a1, is less than equal to the corresponding bit in the y, the a2 is less than equal to the corresponding bit, the b2 in y, and so on, so on. If this relationship correspondence is followed, then we say that x is related to y in the set Bn. For example, here 0, 1, 1, this is, I am taking the bit string of length 4, is related to 0, 1, 1, 1, because 0 is less than equal to 0, 1 is less than equal to 1, 0 is less than equal to 1, 1 is less than equal to 1. Because for k equal to 1, this one, for k equal to 2, and so on, so on. Right? The 2 strings, this one and this one, are not related. This is another example over here. I'm just highlighting that. This is another example in which the relationship is not valid. The 0, 1, 1 and itna are not related. since 0 are not related. Then 0, 1, 0 is less than or equal to 1 is correct, but the 1 is not less than or equal to 0. So this is not related to this. Reverse way, 1 is not less than or equal to 0. So this is also not related to this one. Means neither the first bit string is related to the second, nor the second is related to the first one. So means these two pairs are uncomparable. They, they are not comparable. And in partial order set, it all happens. A pair of set may not be comparable altogether. And that's why it is called the partially ordered set. However, every n bit long string is related to itself. You pick up any string over here, the A1, irrespective of the 0 or 1, it will be related to A1. A2 will be less than or equal to A2. A3 will be less than or equal to. The every x is related to itself. Every y is related to itself. So in that case, for all x belonging to Bn, x is related to x. So once this here we can show that this relation is reflexive because of this one. If x is related to y and the y is related to x, correct? So in that case, x and y both needs to be equal. I hope everyone will agree with this statement. If x is related to y and the y is related to x, according to this definition, then the x and y is bound to be equal. Am I right?
Yes, sir.
In that case, the relation is the antisymmetric. And it is transitive as well. If A1 is less than or equal to B1, B1 is less than or equal to C1 of the another element Z, then the A1 is bound to be less than or equal to C1. And hence this relation is transitive as well. And because this relation is the reflexive, it is antisymmetric, it is transitive, it is a partial order relation defined on. Obviously, this relation, assuming that our participants are well aware about the set concept, I am not deliberating much on that. So this less than or equal to, this is a partial order relation on Bn, and therefore this pair, the set equipped with this partial order relation is a poset. And this poset can very well be represented in this diagram. This is for the set, and this is for the corresponding bit string. So let's see, this is the bit string. Here with the relationship as we have defined, this is the relationship of the set containment in the first one, the left hand side, in the right side, the way we have defined. And this arrow bar, this simply represents 110 is related to 111. The other way around is not true. This is not related to this one. Means especially which is below is related to the elements which is coming above that. Correct? And the element which is coming above is not related, especially above, is not related to the elements which are below it. This one. And similarly, the elements which are at the same level, like here, this one, this one, this one. Similarly, this, because of the diagram problem, this one, this one, this one are at the same level. 1, 0, 0, 0, 1, 1, 0, 0, 1. And similarly, this is the 1, 1, 0, 1, 0, 1, and the 0, 1, 1. All are at the same level. The elements at the same level are not related among themselves. So the A is not a subset of this one, B is not a subset of this, C is not a subset of B. So they are not related under the relationship of the set containment. But A is a subset of AC, A is a subset of AB. So this is a subset A is related to the subset AB, subset A is related to the subset AC. Similarly, 1, 0, 0 is related to 1, 1, 0. 1, 0, 0 is related to the 1, 0, 1. But the 1, 0, 1 is not related to 0, 1, 0 because 1 is not less than or equal to 0 and the second one is not less than or equal to the second 0 over here. So these three elements are not related. So this we call it the hash diagram of the poset, which represents how this pictorially it can be represented. So this is the poset, means once we have a set Once we have a partial order relation defined on it, then the set contain together with the partial order relation, this defines a poset. Now, once we have a poset as a structure, from that, just see, we are defining, there are the 2-3 bounding elements, which I would like to skip it, because even without that, we can explain the concept. So now suppose we have Ax and Y, the way the Ax and Y is defined over here, A1, A2, A3, A4, just using the same definition. It's just we are defining this an operation, we call it meet in the let, and in the Boolean algebra we call it AND. So let us first see, this is the meet, or in the poset language bounding elements, we say that this is the greatest lower bound of the subset containing X and Y. I'm repeating, the meet operation or the meet element is defined. Meet is between the two elements, pair of elements. So this is defined as the greatest lower bound of the pair of elements containing X and Y in the set Bn, the Bn which we are considering over here. Let X and Y be the another bit string of the length n. And how we are defining it? The every Ck, like the C1, C2, C3, the in general Ck we are writing, this is nothing but the minimum of the corresponding bit string. Means the C1 will be minimum of A1, B1, C2 will be the minimum of A2, B2, Ck will be the minimum of AK, Bk. For example, the 0, 1, 0, 1 meet 0, 1, 1, 0 will be defined as the minimum of 0 and 0, first element is the 0, minimum of 1 and the 1 is the 1, minimum of 0 and 1 it is the 0, minimum of 1 and 0 is the 1. Means meet of these two is going to be, I will explain all in the bit operation itself. And the meet of the 1, 0, 0, 1 and the 1, 1, 0, 1, the 1 and 1. The minimum of that is the 1 is written over there, 0 and the 1, minimum is the 0 is written, 0 and 0, minimum is 0, it is in there, 1 and 1, minimum is 1, so 1 is over here. Correct? It means meet symbol is used to represent the Boolean AND operation. You can very well say, if we 0 and 0, it is a 0, 1 and 1, it is a 1, 0 and 1, it is a 0, 1 and 0. So this is the meet operation what we are using in the lattice. We are using over here. I hope it's okay. Similarly, the join operation, X join Y. Join operation over here. So this is defined as where Ck is the maximum. So instead of taking minimum for the meet, we are taking the maximum for the join operation. So like this one, the 0, 0 maximum is 0, so 0 is written, 1 and the 1 maximum is 1, it is written, 0 and 1 maximum is 1, and so on, so on. It means join operation is nothing but the Boolean or. 0 or 1 is the 1, 1 or 1 is the 1, 0 or 0 is the 0, and so on, so on. The complement of, let's see, complement of the X. If we define as the C1, C2, Cn, X is the beta string of length n, then the Ck will be 0, means the C1 will be 0 if the corresponding bit in the Ax is 1. If Ak equal to 1, and the Ck will be 1 if the Ak equal to 0. Means just flip the bit. If it is 0, make it 1. If it is 1, make it 0. Whatever the resultant bit string you are getting, that will be the 1's complement, the complement of the X. For example, this one, the 0 has been converted to the 1, 1 flipped to 0, 0 flipped to 1, 1 flipped to 0, and so on, and so on. So these three operations we are defining. Now let us see here, come back to the diagram of it, the next diagram itself. Just see, again the same diagram, I'm repeating. here in the bit string, what we see that, you see the diagram over here, this is the arrow representing that. So 1, 0, 0 and 0, 1, 0. If we make the or the union, like the A and the B union, so we are getting this one. This is also related, this is also. Similarly here, 1, 0, 0 and the 0, 1, 1. If we make it the OR operation, the 1 and 0, 1, 0 and OR 1 is the 1 and 0, 0. So this is the OR we are getting. The pickup, what I meant to say, you have pick up any pair of elements, either here or here. You will have a meet of the elements in the set, sorry, join over here, and the meet of this one in the set itself. Means in the modern algebra concept, we say this structure, if we take the meet and the join as the two binary operators, then any poset which is closed to the meet and the join is called a lattice. Simple definition. Any poset which is closed, which is closed, which is closed under the binary operation of the meet and join, we call this a lattice. So this poset is also a lattice. This poset is also a lattice. So means any poset which is closed under the operation of the meet and join is called a lattice. Now we see there is another property. Every finite lattice, like this is also a finite lattice. How many elements are there? 8. How many elements are there? The 8. So this is the 8 element. The 8 elements over there. So because number of elements is finite, so this is a finite lattice. This is a finite lattice. And the finite lattice, in that case, there is a one also the bounding element. If it has the, we call it here 0 and 1 element, but the 0 and 1 is not this 0 and 1. Means any which has the greatest, the upper bounded, and which is the lower bounded. Means taken the entire poset or the lattice together. If it has the greatest greatest lower bound and the least upper bound and the greatest GLB, greatest lower bound and the least of the upper bound, then we say that lattice is bounded. So here the greatest of the lower bound and this is the least of the upper bound. Similarly here, this is the least of the upper bound, which is bounding all the elements of the set, including itself. Similarly, this one, it is the least, the lowest of all the elements of this lattice. Means it is bounded, it is both the top element as well as the least element. That is the last element or the first element over there. So this lattice is called a bounded lattice. The any finite lattice is basically a bounded lattice. There is a theorem as well. Every finite lattice is a bounded lattice. Another one, since Boolean AND distributes over the Boolean OR and the otherwise always well, the Boolean OR distributes over the Boolean AND, the corresponding operation, that is the meet and join. So here the meet and join distributes, meet distributes over the join and the join distributes over the meet. In all this, in both the set, so we say that this lattice is bounded, this is distributive, and you pick up any elements of this lattice, we will have a complement of this element in this lattice itself, like the 0, 1, 1. And the complement of that is the 1, 0, 0. 1, 0, 0 is here. The complement of the 0, 0 is the 1, 1, 1, which is also present over there. Complement of 1, 1, 0 is the 0, 0, 1. It is also there. Means we say that every element of this lattice has a complement in this lattice itself. So if the lattice possesses this property, like yeah, it is bounded, it is complemented, and it is distributive, then we say that this is finite Boolean algebra. The bounded, distributive, and complemented lattice is called a finite Boolean algebra, and it is of special importance in the area of computer science, because the very first thing what is taught in the computer science is the Boolean algebra, finite Boolean algebra. Now you see, so this is a finite structure of the finite Boolean algebra. This is the structure of finite Boolean algebra. And see how this is converted into the circuit designing, and how the concept helps in optimizing the circuits, means that using the minimum number of fundamental gates, we can design the implement the complicated Boolean function. So this is the one.
Sir, I just want to ask one thing.
Yeah.
You are just defining the AND functions and the OR functions. But how can you actually basically define? Can you give me a definition of how will you define the XOR function?
X or
The XOR function.
acha, that one. XOR function, basically here it will be defined as the combination of the OR and the one flipping the Boolean. That I am coming to that one. And
Okay.
once we describe this some function, the XOR function, how we are going to just implement in the circuitry. So basically we have only three fundamental gates, like the AND, OR, and the inverter.
Acha,
And
that means you're
using
going to basically define the XOR gate with respect to these three
yeah,
fundamental.
we will be defined XOR using that.
Can't there be any specific these functionalities as something like the from like the this what do you say, the mix man and what these complement functions? Is
Yeah.
there no exclusive function which you can define the XOR function?
Yeah, no, it is not direct like that. During the evolving of this concept, so just say that I'm talking the evolving of this concept using these three fundamental gates, the three
Okay.
fundamental operations, we can define, like just see, we have one operation of the symmetric difference in the set theory. Am I right?
Yes, sir.
But the symmetric difference is basically defined from the union and the complement itself. If you agree with me.
Yes, 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 yes,
Correct,
yes,
so only
yes.
the complementation and the union, two primary this fundamental operation, using that, or the intersection, using that we can define any complicated operation in the set theory. Correct?
Yes, yes.
Similarly, in this Boolean algebra, using these three fundamental gates or fundamental operation, that is the logical OR, logical and the complementation, we can define NAND, NOR, XOR, and so on, so on. Is there other complicated?
Okay, sir.
I'm
Thank you.
going to discuss. I'm going to discuss. What happened? I hope this window is not visible. Is it visible?
No, sir, not visible.
It's not visible, no? Okay.
Yes.
Just 1 minute. Let me share.
Okay.
Okay. What happened? Why is just 1 minute? Just
Okay, sir.
What happened? Why slide is not sharing? Just 1 minute. Let me come out. Just 1 minute. I will just join it.
Yes. Sir, again rejoin.
You were saying something. Is it visible?
No, sir.
No.
No. No, sir.
Why I'm trying to share it. Now is it? I hope it's okay.
Yes, sir.
Correct? So I hope this circuit is visible.
No, no, sir, not visible. Just we will getting the message you are presenting to everywhere.
That's why you stop me to Google sharing in the window. That's what I have done it. Sharing to everyone.
Sir, first you open your slide.
It's already open.
Okay, then from this one you go to the share window. When you click the window, you will see your slide, and then you
That's
click.
what, that's what I am doing, Ratnaji. That's what I am doing. I see the saying, yeah, we will go to the sharing a window. Stop. Now I hope is it visible? It is showing on
No,
my
it's
screen.
not visible.
Actually, sir, the visible thing is that's written you're presenting to everyone. That's message we can see.
Sir, I believe you are presenting the, sir, you have chosen the, while presenting, you have chosen the internet, the Explorer. The application you have to choose is the PPT, the power, Microsoft PowerPoint.
No, no, Chintan, that is not a problem.
And I have that is not a problem. Okay, just 1 minute. Just 1 minute. Let me check it.
Actually, there are some option. Either you can show your entire screen, and
Screen or window, correct
yeah,
na? Or
yeah.
window. The
But my
window I am
both,
showing.
yeah, just you can also do share entire screen. Also, you can share.
Entire screen I am sharing it. Share, correct? 1 minute just. Present entire screen and then share. Now suppose I am presenting it over
Yes,
there.
sir. Visible, sir.
Now visible na?
Yes, sir.
It's okay. So let us see. Sorry for interruption of the 5-6 minutes.
Okay, sir. It's okay.
So now after just defining the finite Boolean algebra, and I will discuss how the different functions, the x or another thing, can be implemented over here. Let us see. This is a function in the n variable. This is the x1, x2, x3, and so on. So basically, this is a function from bn to b, bn to b. Means the n inputs are there and the output is going to be either 0 or 1. That is the function. The entire Boolean function is just represented and the entire circuitry is designed using this concept. So this is a block diagram of a broad Boolean function. Consider a 2 variable function and a 3 variable function. In the next slides, I will show you. And let us this. I hope now I am enlarging it so that it should be visible to all of you. This one. So this is the one Boolean function x, y. So consider a two variable function b to b as given in this, the first A. We can write the function f x y. Just see, this function is simply whenever the x is 0, this function is outputting 1. And whenever the x is 1, 1, it is outputting 0, irrespective of the y. Irrespective of the value of the y, this function is nothing but the simply inverting the x. This is the another one. Here the function b2. Again, this is the b2 to b. The x and x. So this is 0. This is the 1. This is 0. This is 1. So this is the another function over there. Now at the time of designing, just see, this is the circuit. What I am trying to say, once we are going to implement, so that this, if it is the B2 function, then in our truth table, or the all possible combination of the input, there will be 2 to the power 2, that is the 4 entries. If there are the n valued function like this one, then in the truth table there will be 2 to the power n entries and the corresponding output. It may be 0 and 1, but the table will have 2 to the power n such entries. Now to implement this in the actual circuit designing, what is that? For every pair of such this one, for every two, we will have to take one fundamental gates. So we can imagine how many fundamental gates will be required. And here, just to implement this, the A, we need nothing, just one inverter, and that too included on the X line itself, and that will serve the purpose. Circuit designing 1, 2, we will discuss it. So means how the requirement of the circuit is minimized. This is another example over here. This is the B3 to B, means 3 input values x, y, z, and the output is either 0 and 1. Just see here that this function, out of the 8 possible combinations, so we have the 1 in only 2 rows, and the remaining 6 rows, they are the 0. So if we have to design a circuit for that, then what we can do, we are not going to design circuit for the all possible combination. We will pick up only this, the 2, which is going to output the 1. So that is the x complement. We can write it x complement and y. Sorry. This is the x complement and the y and the z, which is giving the or. This is the last one, x, y, and z, x, y, z. So we need only, once we represent it, I mean the function is going to represent the 1 over here, and the remaining value will be 0. If we need a 0 for that, then only we will have to put one inverter after that one. Only one in Hello. Now just see, this is another function, the truth table for the Boolean function. This is the 3, and this is the x, z, bar, y. So this is the function here. This is the, I hope this is the truth table is, we all are comfortable with that. X, y, z, and for this function. So because there are 3 variables, there will be 8 entries in the table, and so on. The corresponding z bar, so whatever the z last column, invert to this one, x, z bar, x and the z bar, we get this one. Add these 2 values, we will get this x, z bar, and the x, y, the 0, 0, and so on, so on. This value we have got. Now you see this one. One, but similarly, given whatever the Boolean function is given, the n input, the 2, 3, 4, 5, or this one, we can always have a corresponding truth table. Using this truth table, we can find how many zeros are there and how many ones are there. So what we do basically at the optimization level, we pick up what is the minimum number of out of the 0 and 1, whether the number of 1 is minimum or number of 0 is minimum. So there is a corresponding representation of the Boolean function, what we call it CNF or the DNF, disjunctive normal form or the conjunctive normal form. So only we pick up the minimum so that the number of fundamental gates required to design that function, Boolean function, the number of fundamental gates required should be minimum. So only for that, whether the 1 is minimum, we go for the corresponding representation. If 0 is minimum, we go for this one. So that same function can be represented using the minimum number of Boolean circuits, fundamental circuits. See this one, the 3 simplest gates. Also we call it the fundamental gates, or the AND, OR, and the NOT. Somebody was asking the XOR and so on. These 3, and using that we can implement all other this one. And these are they correspond directly to their respective Boolean operators like the AND, OR, and this one. These are the circuit designing. Just see, this is the one of the diagram which we have done. If we just design a truth table, then for that, because the 3 variables are involved, we will have the 8 entries in the corresponding truth table, and there will be 8 possible outputs. So for the 8 possible such combination, we need much more number of fundamental gates than this one. But once we have the truth table and we have picked up what we actually need, where the ones are required, we can just implement this one using this 3 number, 1 AND gate, 1 OR gate, and 1 inverter. Using that, we can implement a function which is the 8 entries in the truth table. Just imagine when a computer is of the 32-bit, 64-bit. 64-bit means the number of parallel wires, and each wire is containing 1 input, 0 or 1. Then that truth table, in that case, in the case of the 32-bit computer, a truth table for one function, I mean to say, there will be millions of such functions to be implemented. For one function, the truth table will contain 2 to the power 32 entries. And if suppose we need the fundamental gate to implement for each such combination, I think the entire Earth surface will fail short of assembling this one. In that case, this your the mathematics, the basic set theory concepts and the truth table, the finite Boolean algebra helps us in optimizing, finding the optimal number of gates which may be required to implement the given function which produce the exactly the same result which is expected from the truth table. So these are the basic things, but we have just done it. How the basic concept of a set theory, correct? With the binary division, the 0 and 1 can lead up to this circuit design, and using that one, the basic, the very large scale integration, the ultra large scale integration, and so on. Just it is because of the mathematics, the discrete mathematics, it helps in the designing that one. The another concept, the Carnot map, the Quinn-McCluskey are there, which helps us in finding the minimum number of gates. But first, this is the truth table, and this translation has to be done in that case. So this is up to the binary. I have kept it up to the very minimum level. If anything to ask here, EXOR, somebody was asking the EXOR. This is the here in the EXOR we can just write hello. I hope the person is there.
Yes, sir.
According
Yes, sir, I'm there.
EXOR, we can write it EXOR over there, and the corresponding truth table here we will make it 0. Make it 0, and the corresponding function we can implement. I hope it's okay.
Yes, sir.
And the corresponding function we can implement it.
Thanks.
Okay. A NOR function is also there. Just after putting one inverter over there, NAND is there just by putting one inverter over there. Okay. So same thing, just a combination means this and this converter we get with the NOR. this and this combination will give you the NAND, and so on. Many other such operations are there. Anything to ask over here? I will go to the another concept related to this one. Fuzzy set breaking the barrier of the binary level to the multi-level. I will just briefly discuss, not in much over here. But if any query up to here, you can please.
So if we go, sir, this is hello. Are
Yeah,
you able to hear
please.
me, sir?
Yeah, please.
So if we go beyond two-element chain, we have seen, for example, if we take a diamond lattice like that, then for a table representation, we may not be having an expression. Is it right, sir?
No, I'm not getting your question, please. Can you please repeat it? Pardon me?
See, this digital electronics is based on two-element chain, that is 0, 1.
Yeah, exactly.
Boolean. Yeah. If we go for like the next one is finite Boolean algebra has 4 elements. 2 next to 2 square is 4. We have diamond lattice. For that, if based on that one, if we define a function, we can define a table-like thing also.
No.
For that,
Yes, yes. Please go ahead. Please,
then see, can we have, for example, here, whatever the table representation give, we are able to find an expression. Is it right, sir? Here, in
Exactly.
two-element case.
Exactly.
Yeah. Is it true for the, if we go beyond a Boolean algebra, beyond 2 elements, that is 4 elements next, 8 elements next, like that?
Yeah, that's what I'm now trying to say after that. This one. Yeah. Now see, before that, just see this diagram I would like to show. Okay? So what happened? Yeah, now the set, whatever the set we have studied, correct? So what we do conceptually, either an element is a part of the set or it is not a part of the set, correct?
Yeah, right, exactly.
In the exchange, either it is a part of the set or it is not a part. I mean, that belongs to or does not belongs to. There is no in between as such.
Right,
but
exactly.
suppose we change this definition to a little bit. Okay? So this definition, suppose X be a non-empty set, and we define a set like here first. Then I will come to this definition. That will be helpful. We define it as the probability. The diagram, just see. The probability of any element belonging to the set is suppose less than or equal to 0.15. Means it is the real value between 0 and 1. Suppose there is another element. The probability of that, the probability of the elements belonging to that set is between 0.15 to 0.5. Correct? Then there is another element, the probability of which it may be between 0.5 and the 0.8. And some other probability is between 0.8 and the 1. So what we have done is, yes, no criteria. Either the element belongs to the set or it does not belong to the set. We have now just made it as a probabilistic. And the element, the belongingness of this, the probability of its belongingness is suppose 0.15. So what we have done, the 2 level, we have just partitioned into the 4 level, 0 to 1.5, 0 to 0.15, 0.15 to 0.5, 0.5 to 0.8, and 0.8 to 1, the 4 level. Now what happened? Now the 2, 0 and 1 itself won't be sufficient to represent this level. So we need 4, one representation for this level, another representation for this level, another representation for this one, and so on. So we need 4 such representation. So for that, we will go something like that. 0, 0 will be representing the first step, 0, 1 will be representing the second one, 1, 0 the third one, and the 1, 1 the fourth one. Correct now? So in that case, we have done is the multi-level instead of the single level. Correct? So, I hope it's okay.
Yeah, right.
So just based on that, we define this is a fuzzy set. So we have to basically change change or the conceptualize, change the concept of the set of the definition. Let AX be any non-empty set. A fuzzy set A in AX is characterized by a membership function. So we define this is the mu A from the set X to a real interval 0 and 1. This is the closed interval. Yeah, if the probability is 0 means the element is not in the set. And if the probability is 1 means the element is certainly in the set. And in between it is all the probability. And mu Ax is interpreted as the degree of the membership of the element X in the fuzzy. Like the degree of the membership, if the mu 0.15, the 0.15 is the degree of the membership of that element in the set X. Similarly, the mu 0.5, mu 0.8, mu 1. So this is the set we say, and we can go for the multiple such level. But the problem comes over here with what I am trying to just think. Yeah, problem comes. Yeah, for the binary level, we have the technology available. Yeah, in the transistor, if a certain level of voltage is there, if the voltage is below that one, then we interpret it the 1. If the voltage is above that threshold level, we take it as the, sorry, above it, that one, we take it the 1. If below that threshold value, then we take it as the 0. So we have to define the corresponding circuitry which implement this, the 4 level of the voltage, because ultimately it has to work with the current, whatever the form, the electrons for the movement. That means we need a supporting the circuitry, the transistor, the voltage which contain the what is called the capacitor and whatever the technology name is there, which holds the 4 different distinguishable level of the voltage. And if the voltage is between this threshold, we call it, it is the high, the 1 it is representing. If it is in this one, within this range, it is the 10 representing, and so on, so on. So we need this supporting. And for that, this is the quantum technology, quantum technique is being used to develop that concept over there. This is the one of the summary. Yeah, in the Boolean logic, in the fuzzy logic, and so on, quantum logic, it's goes over there. Correct? So any query, now it is open for that. A little more slide is there. So we'll discuss that. This is to wind up. We started with the basic element in the set and added to this fuzzy and the quantum mechanism over there, quantum fuzzy circuit model. So we need that. Yeah, this the any point on the Bloch sphere. We call this the Bloch sphere. It's just to measure any point, because we are going from the discrete to the continuous concept. So if any query, any such related to this one, I will be happy to answer that. Any such query? Should I put the slide back on the? So this is a very good what I have tried to present today. Hello. Yeah, query, any query please? I have tried it to the keep it to the minimum level. Yes, Ganesh Dharmadhikari, any query please?
Written no queries.
No query, I said. So I hope people must have enjoyed. I have tried how this evolution from the basic, from discrete mathematics point of view, to explain how this concept is important in the digital electronics, why this topic is taught and why it is important in your the engineering and the science concept, why this discrete mathematics is one of the integral part over there. So basically, besides the other concept is there, but the one how this is the basic state concept has led to the evolution of the current technology of the computer, supercomputer, and so on. So this all has evolved. So that one I have presented. Now anything, we have the enough time, 10-15 minutes. Any query, you can very well. We can discuss on that if any query is there.
Chintan Mandal, you have any queries? So ask, sir.
No, sir. Thank you. Thank you very much. Thank you. Thank you very much, sir.
From participants,
Can you show the last slide, sir, please?
Yeah, just one. This one.
Yeah, right.
Yeah.
So you mean to say that this fuzzy as well as the quantum fuzzy circuit model, both are practically now it's happening. You mean? Can I
Yeah,
understand like that?
yeah, it is happening. People are working on that, and there is some quantum computing devices that has come into the lab stage only, because of which
Oh,
is the technical thing. It is already in the lab stage, and a lot of research is going on in the quantum computing.
okay.
And because this one, I think once it is implemented, it will be very helpful in the machine learning and the artificial intelligence, because it all works under the concept of the fuzzy logic.
Yeah,
So
I mean,
then
we can expect a device like the circuits we see, very large integrated circuits like that. We can use these ideas in designing those things.
yeah,
You mean?
exactly. That's why this is the research. Science and the mathematics has the beauty. Basically, it gives you the theoretical foundation. It proves what is the theoretically you have conceptualized, whether it is correct, conceptually is going to be correct or not. And once it is proved, the mathematics helps in that. Yeah, and once it is, then you go for the implementation at the technology level, and that's why it is happening, the quantum computing. It is quite possible. You can have the multiple, because if you recall, uh, should I stop sharing it and come face to face?
Yeah.
Once you just, one of the example I'll show you, that is the digitization of the wave, the communication, what we are doing it. Yeah, this is what is called wave form, analog to digital, correct? So basically, level of quantization has helped in speeding up the entire communication, using the limited bandwidth, how the more and more information can be pushed over the same communication channel bandwidth. So that digitization has helped. The same concept, they say the fuzzy logic is just basically helping in the conceptualization of that, how many level of the digitization of the belongingness and not belongingness we can have, and can we have the corresponding hardware and the technical implementation to implement those concepts or not, and in between the gaps. You should not fluctuate. Yes, sir.
Yeah. Thank you.
Yeah. So that we can. Any other query, please?
Sir, can you share some of your experiences? Like we face some difficulty, like how to manage between teaching and research. So when we prefer teaching, or research is hampered, and when we focus on research, then teaching is compromised sometimes. So can you tell something like motivating things to how to manage these things?
Should I tell it the positive notes or the negative notes?
Sir, of course, positive note. No, I didn't understand why are you asking, because this is my problem. So Sir, this is my problem. That's why I asked it.
No, just be practical.
Yes, sir.
Actually, in India,
Yes, sir.
I'm telling a little bit of the sad part. Again, a sad part. In India, the scientific and the research ethos lacks a lot. And you will find very few people who will be encouraging you to do such things. Particularly our teaching community. I have spent around the 6 years as a full professor and dean of the institute. Because our faculties are, even including the government institution and the private institution everywhere, they are burdened with a lot of other tasks other than the teaching and research. This is means these days you're the NAC is there, NIR up there, the NBA is there. These people have overburdened our the teaching community to such an extent. Keep on filling this garbage in the form of the documentation to fulfill their thirst. And just this has nothing to do with the research one, whether you are doing research or not, but you should have some ready-made title to fill into that. So what is required here? If you are motivated, it is your responsibility to find time from your this busy schedule, teaching plus the whatever the non-productive job you are doing as a part of the job of the academic institution. So that is the reality, and we have to face with that. But I mean, if you go in the external, the foreign country, they ask you, whether you want to be in the full-fledged education or you want to opt for the research. If you are opting for the research, then your teaching load is reduced to a maximum extent. So hardly 4 or 5 lectures you will be given in the week. The remaining time you can devote on that. If you have opted in a full-fledged, I want to be in the academic, then you will be given load like the assistant professor, then the 18 hours, the associate professor 12 to 14 hours, and the professor full-fledged 8 to 10 hours, plus some the research students, the Ph.D. students to guide with that. So here in India, irrespective of the institution which we are working in, there is no such criteria. There is no such bifurcation. If you have to get some project from the ministry, you have to get some, you have to do some, many other things are there. So means sole responsibility that you will have to find your own time. Get motivated, remain motivated, do some research, get it published. If you are not finding the work getting published in the reputed journal, okay, no problem. Go to the second year and so on. Don't get initially disheartened. Okay, it has not been accepted in the SCM or the IEEE and so on. No problem. Time will come. It will get accepted. Initially, keep on doing, keep on get associated with that. So you will have to find your own time. Your institutions, I'm sorry to say, even you're the boss, is not going to spare time for you. Yeah, the phenomena is all over India. This is the phenomena. So we have to live with the reality, and we have to do that. I hope I have not criticized too much. I have told you the reality of the life, what we are facing.
Yes, sir.
You will have to find your own time. Even in the research institutions, the very few are there in India which encourages you to write papers and do some research. Otherwise, I will encourage you to read a book written by the APJ Abul Kalam Azad. He has written about his life, the India in 2020 or so on. He has written that. He has narrated his own story and all. Everywhere the people are facing the situation. But only thing, your own motivation level, your own dedication level will help you in finding time, keep on publishing. Many people, once you are doing some research, then somebody will come, what are you doing? Come on, man, you do this thing, you do that thing. One example I will tell you, in Germany, one of my friends was saying that, in the canteen, if in the university, I hope many present over here might have, if they have gone, they might have faced the experience. If you are just taking any professor or the teacher in the university, if they have visited a canteen, they have taken some tea or snacks, and suppose he has stepped out of the canteen without paying it on the counter, then the canteens are advised by the administration over there, don't disturb the professor by asking for the payment. Let him go out, just you note it down, and charges that will get deducted from his salary and it will be paid to the canteen. What is the idea behind that? Idea is that the professor might be in the thinking modes. You might be thinking something. If you ask for the money, that thought process will get disturbed and that research will get hampered. See the scientific temper of that level and see the scientific temper. They will catch a hold of your collar. Just pay and then you move from. In India, if you are not paying and moving out, then they will catch hold of your collar and they say that you first pay and then you move out of that. It is scientific temper I'm talking about. So that needs to be developed. I don't know when that will get developed. But one person was saying that in the same Germany, in the tissue paper which is lying on the table in the canteen, if you have written something and if you have thrown it that, and if the sweeper comes, and if you find that in tissue paper something is written, he is not going to throw this on the dustbin. He will simply just flatten it and keep it on the table with some weight over that. You may be somebody else will come and start from that equation or not. That's the scientific temper they are living with, and what we are doing. So that it is you who will have to remain motivated for that. You will have to remain motivated for that.
Right. Thank you, sir. Thank you very much.
So,
May I request?
Video on if possible, and we will take some slideshow photo. So we will take some snapshots for our.
any other query, please?
If there is any query, please ask. We still have some time.
So should we wind up, Ratneshji, now?
Yes,
I
sir.
hope I have completed in time.
Okay. Yes. Thank you very much, sir, for a nice lecture, which will be very fruitful for our participants. So I think 11:15. Okay, sir. Welcome back at 12 noon for validatory function.
Okay. Thank you. I think the 10 minutes break is required.
Thank you very much, sir.
Okay. On the same link, Ratneshji?
Yes, sir. Same link.
In fact, you can stay online also. You can take a break, but stay online. There is no problem.
Okay.
Okay.
Thank you, Ratnesh sir.
Thank you, Atriji.